Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 7, Differential Equations. Today's topic is 7.3, where we're talking about how to sketch slope fields. Enjoy today's notes. All right, welcome to 7.3 Sketching Slope Fields. As we begin this one, we're going to do some separate notes off of this sheet to try to introduce this section. So I'm going to scroll up here to a blank piece of paper, and you might want one as well as we're going through this. So once again, 7.3 Sketching Slope Fields. We're going to start off with the concept of what a slope is, right? We've been talking about slope pretty much this entire year, but we know that slope from back in like Algebra 1 or like 7th or 8th grade, we know is generally the rise over the run, right? It's the slope of like a linear function would be the rise over the run, or the change in y over the change in x. Now in this class in calculus, we've learned that there's this thing that's called a derivative. We've learned this thing that's called that there's this thing that's called a derivative, and we know that from chapter 2 that the definition of a derivative is it is the slope of the tangent line of a function at a given point. So it's the slope of the tangent line of a function at a given point. And we've spent a lot of time this year talking about derivatives. All the chapters from chapters 2 through chapters 5 were all about derivatives and slopes. And so this is a very, a concept that we've talked a lot about this year. So today, to introduce this, we're going to talk just quickly about like what little slopes look like. What we're going to do is we're going to make a quick table. So here's our quick table, and I'm going to just say what is the slope and what is the graph look like. And we're going to do some things like we'll say, okay, we'll do -3, we'll do -2, we'll do -1, 0, 1, 2, and 3. And what I'm curious about is I just want to have this exercise where we're thinking about what does a line with that slope look like. So for example, if I have a slope of 0, what is that going to look like? Well, we know that if the slope is 0, it has no rise. It's neither going up or down as it's running to the sides. And that is a case where we have a horizontal line. When we have a slope of +1, we know that, for example, that the slope should be going up 1 and then right 1, and so we have a slope line that looks like this. If we have a slope of 2, it's going to go up 2 and then right 1, and so we have a line that looks like this. And then if I have a slope of 3, that's going to be going up 3 and then right 1, so we have something that looks like this. What I'll just notice is, when we have a slope that's 0, again, we start with a horizontal line. When we have a positive slope, obviously it's going upward as it goes right. But we can notice that as the slope increases, that these lines are getting steeper and steeper and steeper. So if I wanted to do 4 or 5 or 10 or 100, that these slope lines would just be getting steeper and getting closer to vertical as they go along. We can go in the opposite direction, though, thinking of negative slopes, noticing that when the slope is -1, we have a slope line that looks something like this. And if we're going to -2, that would be like going down 2 over 1. So we have a line that looks something like this. And then if we have a slope of -3, we'd be going down 3, right 1. So we have something that looks like this. So similarly, what we notice that as the slopes get more negative, they're getting steeper and steeper and steeper as well, just in the negative direction. The idea of these little lines is going to be very central to what we're talking about today, which is this idea of a slope field. Thinking about visually, what do these slopes look like when I say, hey, a slope of -2 would look something like this. A slope of +3 would look something like this. We're going to keep that in mind as we enter today's notes. So let's do that. So today's notes, 7.3, sketching slope fields. A slope field represents a differential equation on an xy plane. It shows the slope of all the particular solutions of the differential equation. Below is a differential equation with its accompanied slope field. dy dx is equal to 2x. Now, what do I notice? What is this? So we see that we've got this graph here, and we see that we've got this equation dy dx is equal to 2x. 2x is a linear function, right? And as I'm looking at this, if I was thinking of a linear function, that would be something that sort of looks like a straight line that's going up. And I'll notice that that's not what this looks like at all. So what is this? What is this slope field? What this is showing us is that various coordinates that are on this graph, it's telling us what the slope of our y function is. Now, we don't know what the y function is. We can find it, and in fact, we're going to find it here in a little bit. But this is telling us what the slope specifically is. So, for example, if I were to pick, say, this point right here, which I'll highlight, and actually I'm going to just use the highlighter for it. This point right here in yellow is the point, looks like 1, 1. So that's the point 1, 1, that little tick mark that we've got right there. Now, what our differential equation is saying, hey, at that point, if I want to find the slope, that dy dx is going to equal 2 times whatever the x value is. So our x value at that point is 1, and so the slope there is going to be 2 times 1, or 2. And what we can see here is that this little tick mark is essentially a little line that has a slope of 2. Similarly, if I were to pick, say, a different point, like this one over here, let's try that one. This point here looks like that's the point -2, -2. If I were to find the slope at that point, that would be like dy dx is equal to 2 times the x value, right? Because our differential equation says it's 2 times the x value. That x value at that point is -2. So 2 times -2 is equal to -4. So at that specific point, the slope of the function of y is -4, and we can visually see that as this tick mark, which as it's going to the right is going downwards. It's got a negative slope, while this one up here had a positive slope. We can notice looking at this slope field that as the x values and the y values are changing, that the slopes are getting different, right? We can see maybe some slopes of 0. We can see some positive slopes and some negative slopes as we're looking at this. But the idea here is a slope field is a visual representation of a lot of different slopes at particular coordinates. So each one of these little tick marks is representing a visual of what the slope is at that specific point. Now, let's take a look at this actual differential equation that we've got. So this differential equation that we've got is dy dx is equal to 2x. We know that in this case, that if we wanted to think about a function that has a derivative of 2x, an example of that might be something like this, where we could say, hey, if we take the antiderivative, that y would be equal to the integral of 2x dx. And what we could do is we could say, all right, well, we can use our power rule, but to add 1 to this exponent. So this is like x to the 1 now. If we add 1 to that, that would be an x squared. And we would need to divide by 2. So that would cancel this 2 out. And that tells us that y here would be x squared. And then because this is a indefinite integral, we're going to have a plus c at the end. So this is what we would refer to as our general solution for this differential equation. If y is equal to x squared plus c, its derivative, dy dx, is equal to 2x. And this would be a visual of the slope at every point on that graph. So what do we notice here, and how can we interpret something like this? I'm going to quickly erase these 2 points that I've got on here. You might have drawn them on your page, and that's fine if they're already on there. But for the sake of this, I'm going to show you what we're taking a look at. Let's say, for example, that we've got, we know that this is our function, y equals x squared plus c, but we know that it goes through the point 1, 1. Let's say that we know that it goes through the point 1, 1. So I'm going to draw my point 1, 1 on my graph. And what we have here is we can calculate the slope at that point. In fact, we already did. We said that the slope here was 2 when we plugged in that x value of 1. But what I'm noticing for these little tick marks that I've got here, these little slopes, is I almost treat it like waves if I'm trying to sketch a function itself. And so what I'm going to do is I'm going to draw that tick mark that was going like this. I'm going to draw that function going upwards with that along those tick marks, and we can see that it sort of goes upward. And if I go in the opposite direction, I notice that the slope is slowing down until it gets to about a slope of 0. where we see that these tick marks, the slopes here are horizontal. So I'm going horizontal with my graph. And then now I'm noticing that the slope is starting to curve upward, going in the negative direction. And so I'm going to curve my graph going upwards in that direction as well. And so I have something like this. Now, two things to notice. If I don't know what the function is, all I'm really doing in this step is I'm looking at these lines and I'm trying to draw my my curve, my function, parallel to them so that they're going along with these lines. Sometimes people think of this like waves in an ocean, where if I have this point and it's following along these waves, the waves are pushing it along, they're pushing it along, and then upwards and upwards and upwards and upwards, as if it's like a current or something like that. That is a common way that people sort of think about it. But once we sketch this, we can actually think back to, well, we know that our function here is x squared plus c, and we, of course, would expect that if we graphed x squared plus c, that it would, in fact, be a parabola. So it makes sense that when I follow that slope field, that it ends up sketching something that is of this parabola shape. Now, why, though, is there this plus c? Well, we know that we could be starting this at really any point. For example, if I said that my curve went through this point right here in green, we could follow that slope field to the left, and I say, hey, it's going upwards. I'm staying parallel to those. I'm going upwards, upwards, upwards. And then to the right, we see it's getting less steep, less steep, less steep. I've got a slope of 0. Now my slopes are positive, so it's curving upwards and to the right. We've got something like this. This is also a parabola, right? These are both parabolas. They just go through different points on the graph, different starting points. And that plus c is essentially, shifting that graph up or down. We could really have any different parabola or any point that it would go through that would give us a different parabola as we scoot this graph up and down. But the defining thing is thinking about what point does it go through. Great. Let's take a look at number 1 for us next. So use the differential equation to create a slope field. Okay. They're giving me here dy dx is equal to xy. So it's the x value times the y value. This is a common thing that we see on the AP exam. Sometimes they'll give you a blank slope field and they'll ask you to fill it in. So what are we being asked to do? We notice that there's all these dots, all these coordinates that are on this graph. What they want us to do is for each of these little dots that we've got here, we're going to take a look at what the coordinate is. We're going to plug in the x and the y, and we're going to calculate the slope at that point. Once we've calculated the slope, we're going to then go ahead and we're going to draw a little line, very similar to what we're doing up here, where we drew those little tick marks related to those slopes that we had earlier. So where do we even start for something like this? What I'm going to do is, we'll start with, say, this point that's right here. How about this point right here? This is the point positive 2, 2. So what am I being asked to do? Well, at that specific point, if I do 2, my point is 2, 2, dy dx is the x value times the y value. So that's going to be 2 times 2, which is 4. Now, this doesn't have to be exact, but I'm going to try to draw a little slope line that's like a slope of 4. That's something close to that. If I go 1 point down, now this point here, I'll keep it in green. This point here is at 2, 1, this point that we've got right here. And if we find the derivative of that, dy dx is x times y, so that's 2 times 1, which is 2. So it's still a positive slope, but it's not as steep as that 4. So I'm going to try to just represent that. Maybe something that looks like this, a little bit less steep than that 4 that was above it. What if I go to this point right here? This point is at 2, 0. So if I do 2, 0, at that point dy dx is equal to 2 times 0, which is 0. We know that something that has a slope of 0 has a horizontal tangent line. And then we can continue on to our points below. So for example, 2, -1 has a derivative of 2 times -1, which is -2. So notice now we're going to do a negative slope, something like that. And then 2, -2, the derivative there would be 2 times -2, which is -4. And so we're going to have a steeper slope like this. So what I've done essentially at each of these points is I've calculated what the slope would be, and I drew a little tick mark on that coordinate showing visually how steep that slope is, if the slope's positive or the slope is negative. Now there are some shortcuts, right? Like in this case, if I were to do this, it looks like 25 different points here. That would be a lot of work. And so sometimes it's nice to try to look for shortcuts to help save you some time. For me, one thing I think about is when is the slope 0? When is dy dx equal to 0? And what I'm looking for here is really, since it's x times the y, the time when the dy dx is going to be equal to 0 is any time when x is 0 or y is 0 for those coordinates. And so looking at that, that's going to be really anything that's on the x-axis, right? Those are places where the y value is 0, or things that are on the x-axis when the x value is 0. So any of those coordinates, the slope is going to be 0, which means we're going to have these horizontal lines at each of those values. These are all places where the slope is 0. And that saves me some time now because I don't need to calculate those like I did over here. That gets rid of a number of my points, which is really nice. But what I can do, and frequently when I do this over time, is I start thinking of these slopes in my head and drawing them. This point right here is 1, 1. So I would do 1 times 1. That's going to give me here a slope of 1, which is going to look like that. This point here is 1, 2. So 1 times 2 is 2. That's slightly steeper than my 1. So that's something like that. 1, negative 1 is going to be a slope of 1 times negative 1, which is negative 1. And then 1 times negative 2 is negative 2, so that is slightly steeper. We're going to have something like that. Here at this point is negative 1, 1. If I multiply those for the derivative, we're going to have a negative 1 slope, like that. Here would be negative 1 times 2, which is negative 2, something slightly steeper. Here at this point would be negative 2, 1. That's a slope of negative 2 as well. And then here, negative 2, 2. Negative 2 times 2 is negative 4, so something like that. Here we've got negative 1 times negative 1. If we multiply those, that is positive 1. Negative 1 times negative 2 is positive 2, so slightly steeper. Negative 2 times negative 1 is positive 2, so something like that. And then negative 2 times negative 2 is positive 4, so even steeper than that. So visually, this is my completed slope field. There's nothing special here about the colors, right? Like if I was doing this, all in like say black pen or something, they'd all be the same. I'm just highlighting here in red these places where the slope is equal to 0. And by identifying that allowed me to not need to calculate as many of these slopes. Sometimes, we might be asked, or we might want to show the work for these if we have a more complicated equation. But otherwise, if you can do it in your head, that's fine as well. But that's problem number 1. Number 2, we've got a different equation. We've got dy dx is equal to y minus 2x. So dy dx is equal to y minus 2x. Again, here in this case, looks like I've got 1, 2, 3, 4 across. I've got 1, 2, 3, 4, 5 going down. So I've got 20 spots on this graph that I'm going to need to fill in with my slopes, right? Like with these little slope tick marks. One way that people sometimes do this is maybe a little bit of an organized way to approach it. But I think this is a good one for you to maybe pause and to try on your own. One organized way that you might, approach this, I'm going to just separate for what we've got for right here, is we might make just like a quick little table, like essentially what we did over here, but with the same idea for this table, and just throw those points in. So what is the coordinate? And then what is the slope at that specific point? So for example, this point that I've got right here, hey, the coordinate is negative 1, 2. So negative 1, 2. The slope is going to be, I need to plug into this equation for dy dx, right? The derivative is whatever the y value is, minus 2 times x. So that's going to be 2 minus 2 times negative 1. So 2 plus 2 is going to be equal to 4. So that's going to have a pretty steep slope that's positive for that. We can then move on to another coordinate, maybe going right below that. This point right here is going to be negative 1, comma 1. So negative 1, comma 1. If we plug in our y value is 1, that's minus 2 times negative 1. So 1 plus 2 is equal to 3. So still positive, but a little bit less steep. Next, we can go on to our next point and just try to be systematic with this where we're hitting each point. If we do the next point down, that looks like this is going to be negative 1, comma 0. So negative 1, comma 0, that would be 0 minus 2 times negative 1, which would be 2. So a little bit less steep. And then maybe we could see that, hey, there's a pattern going. Maybe probably the next one here is going to be 1, and then probably the one below that would be 0. So something like this maybe as well. And so if you see the pattern, you can try to continue it. I'm noticing that those are just decreasing as I go down as well. Again, this is a good time for you to pause and to try to fill out the rest of the slope field on your own. Take a moment and see if you can do that. All right, welcome back. Hopefully you tried to fill in the rest of your slope field here. Again, this is about what I got. You might have gotten something slightly, your tick marks might not be angled exactly the amount, but what we'd be looking for really here is just places where the slope is 0, where we've got some positive slopes and where they're getting steeper, and where we've got some negative slopes and where they're getting steeper here. But again, as I was filling this out, all I was thinking about is what's the coordinate? So for example, at this point, this is 1, comma negative 1. So the slope there would be negative 1 minus 2 times 1. So that would be negative 3. And I drew a little tick mark that looks like a slope of negative 3 for me for this. You're going to do that at every single one of these coordinates until your slope field is filled out. So take a moment to check your work and see if you need to adjust any of your slopes. Sometimes, again, at the beginning, as people are beginning and learning how to do this, it might be helpful for you to fill out your table so that you're being systematic and plugging into your equation, finding those slopes as you go along. But again, generally, as you're getting more and more used to this process, you might just do that math in your head, or say a calculator if you had access to that, depending upon which part of the test that this is showing up on. Great, let's move on to number 3. The figure below shows the slope for the differential equation dy dx is equal to 1 minus xy. So this is our slope, or rather our differential equation, dy dx is equal to 1 minus xy. Let f be the function that satisfies the given differential equation. Write an equation for the tangent line to the curve y equals f of x through the point negative 1, comma negative 2. So what's this asking us to do? It's asking us to write an equation for the tangent line. We've been doing this all year, and we know that our go-to method in AP Calculus is to use point slope form for writing the equation of a tangent line. And that is the y minus y1 is equal to m times x minus x1, right? That is our point slope form. Anytime you're writing the equation of a tangent line in AP Calculus, you're going to probably want to use that form. And again, the reason why we do that is it asks us for two things. What is the point and what is the slope? Well, luckily for us, they told us the point. They told us the point was negative 1, comma negative 2. What about the slope, though? Well, the slope we know is can be found from the derivative of our function, and they actually gave us that derivative. That's our differential equation right here. So we're going to use that equation, that dy dx is equal to 1 minus xy, and we're going to plug that coordinate in to find out what the slope is at that point. So that's going to be equal to 1 minus the x value, which is negative 1, times the y value, which is negative 2. So that is 1 minus negative 1 times negative 2 is 2, so that's 1 minus 2, or negative 1 for that specific point. So what is our equation for the tangent line? Now that we've got our point and our slope, we're going to plug into this form for that tangent line. That's going to be y minus negative 2, so that's y plus 2, is equal to our slope, which is negative 1, times x minus negative 1, or x plus 1 for that. So that would be my equation of the tangent line. In this case, interestingly enough, it doesn't really look like we didn't really need to use the slope field in this particular function, but I want to visually tell you what we're trying to find here. Essentially, what are we trying to find? So the point that they gave us was -1 comma -2. And if we were to try to sketch the solution for this, if I followed those waves, it sort of looks like I've got something that maybe is going like this to the left, and then something maybe going down here, and then as I follow these slope field lines, maybe something that looks like this to the right. So my solution that goes through that point is going to look something like this. Maybe it's not exact, but if I follow those slope field lines, we've essentially got something like this. And I'm going to take this a little bit of a step further. I wouldn't normally need to do this in a problem, but I want to illustrate what we're doing here. Right? This is the tangent line for the function at -1 comma -2, which is this point right here. If I go back to my Algebra 1 skills and I try to get this y by itself in this equation, right? This is the same thing as what y plus 2 is equal to, if we distribute, -1x minus 1. And then if we subtract 2 from both sides, we get y is equal to -1x minus 3. What is that? Well, here's -3, my y-intercept. And if I have a slope of -1, we're essentially going to have something like this for this tangent line that we drew. And again, we know that a tangent line at a specific point should have the same slope. And so what I'm saying here is that this red line is the tangent line at this point -1 comma -2, and visually that appears to be the case. So we can sort of visually confirm and check that what the equation that we made makes sense for the given slope field that we've got, and for this particular solution that we've sketched here. This is not something that it asked us to do in this problem, but it sort of connects what we're doing visually, which is sort of nice. All right, we're going to move on to the final page that we've got here. Problem number 4, final problem for today. Below is a slope field for which of the following differential equations? This is a super common AP exam multiple choice question where they give you the graph of a slope field and they say, hey, which of these equations is that slope field? Where are you seeing these derivatives? So, where do you start for something like this? Where do you even go for something like this? What I notice, so what I'm looking for first is I'm looking for places where the slope is 0. So taking a look, I'm seeing these horizontal tangent lines on pretty much all of these pink, like these things inside of the pink highlighter here. I'm seeing that they're all going straight across. They've got these horizontal tangent lines. And so these are places where the dy dx should be equal to 0. And what I notice is that these are all places where the coordinate, for example, here is x is -1, the y is +1. Here is x is -2, the y is +2. They're all places where the x and the y are opposite signs from each other, which is interesting. After that, what I can do is I can take a look at the actual points that I've got, and we can try to calculate, if we plug in, does it make sense with what we're seeing? So for example, we see at this point here, -2 comma 2, that the slope is 0. So for example, I know that at -2 comma 2, I see that dy dx should be equal to 0. If I plug that into this equation, if I plug in the x value, right, this first equation that we've got depends on just the x. If I plug in the x value, which is -2 in for this, we'd have 1 plus -2, which would be -1. That's not equal to 0, so it cannot be A. It cannot be that one, right? From plugging in the x value that we know that we see from that graph, this equation doesn't make sense. It's not giving us a derivative of 0 for that. Similarly, if I plug in -2 for this, we would have -2 squared, and that gives us 4, which is not the same thing as 0, so it cannot be that. If we do that for C, if we plug in our x and our x here is -2, our y is 2. If we add those, we do in fact get 0, so this is a candidate, could be that one. Here, if we plug in our -2 and our 2, -2 divided by our y value of 2, that gives us -1. That's not 0, so that's not going to work. And then here, if we do the natural log of 2, that does not give us 0. It's not equal to 0, so that's not going to work. So the only one of these that can possibly work or make sense would be C. And again, my idea here is I'm just picking some points here that I can clearly see what the slope is. It's really easy if you pick ones where you see the slope is 0, identify what that coordinate is, and try plugging it into those equations to see which of those work and which of those don't work. One other comment that I'll make on this one is we also said that we noticed that there was a relationship between the x and the y being opposites of each other, right? And so if our x and our y are opposites of each other, if you add them, they're going to give you 0, and that makes sense in this case for this equation. Additionally, what I'll also mention is that the we can identify those slopes at specific points, but really we want to take a look at places where they're positive or negative, or you might be looking at places where the slope is vertical, right? We might have something where we're dividing by 0. That is like really useful things. In fact, I'm going to mention that here on the side. I am looking on that graph for places where the slope is equal to 0 or it's vertical. So that would be like places where the slope is like maybe undefined or it's approaching, infinity or something like that. That's a really useful thing as you're identifying these slopes. Great. That's our last problem for today. Try some of that practice, check your answers, and have a great rest of your day. Take care.